So the talk that I've prepared for today is not a technical talk, but basically a talk that steps back a little bit to look at the research that we do on continental rift zones and the rifts that we find on rifted margins, and to understand the importance and the implications of the work that we do for economic fluids in rifts. So the title of my talk is Structure, Stratigraphy, and Geodynamics of Rifts, Implications for Subsurface Energy. And again, here I'm going to look today at socio-economic impacts of the research that we do on rift zones. So I work at Los Alamos National Laboratory, which is located in the small town of Los Alamos in northern New Mexico, as you can see on the map towards the lower right. So what I'm showing here is a vertical cross-section through a continental rift zone, and this is just an imaginary rift. And I'm going to use this to explain some of the points that I'm going to make today. So from the bottom to the top here, depth to the surface, what we see is a basement. On top of that, we find a shield and a sandy shield in the yellow, a little bit of conglomerate towards the left here, a sandstone in pale yellow, a salt and evaporite layer in the pink and the light blue, and then a clay layer on top. So for petroleum exploration and production, and I think we're all familiar with that, it is very important that we have a thorough understanding of the stratigraphy of the rift basin. So we need to know whether there's a source rock present, a reservoir rock, and a cap rock. And through the dynamic evolution of the rift basin, whether they were all in place in order to generate petroleum. So we need to understand the structure of the rift basin well for migration pathways, the thermal structure and thermal history of the rift basin to understand where the maturation of keratin has taken place. And then, of course, the subsidence history. So the vertical history is really important in all these aspects. So when we produce oil and gas, we always produce water. This is called produced water. And this produced water is brine, and it may have critical minerals in it, for example. A lot of the times, what we do with the produced water, we need to get rid of it. So we re-inject it into the subsurface. This re-injection of produced water may create induced seismicity, which is a hazard that we would like to avoid. So also for the re-injection of the produced water, we need to have a thorough understanding of the stratigraphy of the rift basin, of rock mechanics. How do the rocks going to respond to the high pressure injection of produced water, and of course the stress fields of the rift basin. In recent I'm just seeing if I skipped a slide, sorry. So at the moment, everywhere on Earth, we're doing carbon sequestration. So that means that we are injecting CO2 into the subsurface in reservoirs that can be depleted oil and gas fields or just permeable layers in the subsurface. What we want to avoid here are leaks. They would be a huge problem. So again, here we need to understand whether we have what the integrity of the cap rock is, below which we inject the CO2, whether there are geologic migration pathways along faults, for example. The stress field needs to be well known. And of course, rock mechanics, we need to understand whether there's any risk of induced seismicity. In recent years, the interest in geologic hydrogen has increased significantly. There are different ways that geologic hydrogen can form in the subsurface. And for all these forms, in order to understand where this geologic hydrogen may form, where it may accumulate, and if we can get it out of the ground, we need to get a very good understanding of the basement below the rift, if that is a source for geologic hydrogen. Perhaps mantle degassing, so geodynamics is important. Again, the rift structure, the thermal structure, especially if we're interested in biological processes and the evolution of the basin. This geologic hydrogen and other forms of hydrogen, we also store long-term, so seasonal. So this is called subsurface hydrogen storage. And also here we want to avoid any leaks. So at the moment, this hydrogen storage occurs often in salt structures. And for that, we need to understand the stratigraphy and the structure of the rift basin really well. And then finally, I'm going to give an example about geothermal energy. So continental rift zones are really good locations for geothermal energy and geothermal power plants. They often have a magmatic and volcanic history. The crust has been thinned and the lithosphere have been thinned, so there's usually a very high heat flow. We need to understand the thermal structure in a lot more detail than we usually do when we study in continental rift zones. And then, of course, the stratigraphy needs to be really well known. So in the remainder of this short talk, I'm just going to go over a couple of examples of these economic aspects of fluids in continental rifts and give you examples of how the stratigraphy and structure play a role in our success or non-success of production. So I'm going to start with produced water. And produced water is, again, this wastewater produced by the production of oil and gas. The map towards the right shows a map of New Mexico, and all the gray dots that almost seem like gray fields are active oil and gas wells. So New Mexico produces a lot of oil. If New Mexico was a country rather than a state, we would be the 7th most oil-producing country in the world. With this production of oil and gas that has increased dramatically over the last decades or so, also the production of produced water has increased dramatically. So we get this oil and gas and produced water mainly from the Permian Basin in the southeast and the San Juan Basin in the northwestern part of the state. If we cannot treat this produced water in large quantities, we need to re-inject it. And with this increased volume of produced water, this has now become a really big topic. And re-injection in the Permian Basin has resulted in the past years in induced seismicity. So that is a topic that people are looking at. In terms of carbon sequestration, that happens often in depleted oil and gas fields, sometimes for enhanced oil recovery. But in general, it can happen in permeable formations in the subsurface. What we absolutely want to avoid with CO2 sequestration are leaks. So we're looking at caprock integrity, often with 3D seismic reflection studies and seismic attributes that give us information about, subtle changes in the caprock that may be very important for caprock integrity. And towards the right, you can see an example. You're looking at the left two maps show top depth of several formations in which CO2 is being injected. Towards the right, you can see seismic attributes that we're using to understand any variability in the caprock or the reservoir rock. Also, understanding the reservoir rock where the CO2 is injected into is very important. So reservoir rocks, they have permeability, but that permeability varies laterally and vertically. And so you can have within your reservoir rock permeable pathways that may influence where the CO2 plume is going to migrate. So those are other things that we're looking at for carbon sequestration. Now, in recent years, natural hydrogen and subsurface hydrogen storage have received a lot of attention. The map towards the right was produced by the USGS. This is a hydrogen prospectivity map. When the USGS put this together, they looked at different components. So the presence of a source of hydrogen in the subsurface, a potential reservoir where hydrogen may accumulate, and a seal. And so different components that we understand well from petroleum systems. There's different generation mechanisms for hydrogen, including radiolysis, serpentinization, and perhaps an organic origin. Many rift zones on Earth, or portions of rift zones, may be good places to look for natural hydrogen or to store natural hydrogen underground. So subsurface hydrogen is stored at the moment, again, in salt caverns and salt domes mainly, because they're well understood and they provide great permeability. I brought an example of a study that I really liked from the Cooper Basin in Australia, and the work that they've been doing there to understand the generation of natural hydrogen, organic natural hydrogen. And so the Cooper Basin, shown on the map towards the right, you may be familiar with this basin. This is actually a rift basin, an intracratonic Permian Triassic rift basin. The map towards the right shows in the colors depth to the pre-Permian basement. And as you can see with the dark blue colors, there are these areas here. I don't know if you can see my cursor, but there's these zones where the basement is very deep. Now, the red dots on the map towards the right show gas wells, and the green dots are oil wells. So from the maturation of keratin, we would expect that organic hydrogen would be produced at depths larger than natural gas, so perhaps in the deepest portions of that Cooper Basin. And then the map towards the left that I'm showing here shows in the colors where, in fact, it's predicted that hydrogen would be generated, and it's in these deepest parts of this Permian-Triassic rift basin.
Jolante, just a reminder, it's 10 minutes.
Perfect. I'll be on time. This is the last example that I wanted to give. It's a little bit longer than the other ones, but just a few more minutes. So in the US, we are going through a geothermal energy boom. And so there's a lot of interest in this topic, also of the new administration. The map that you can see towards the right is a hydrothermal and enhanced geothermal favorability map that was put together by the National Renewable Energy Laboratory. The colors that you see here, the dark red colors, are areas that are more favorable for geothermal energy. And the tiny yellow dots that hopefully you can see are places with basically proven hydrothermal sites. So for geothermal energy, if we're looking at favorability, we're looking at different geologic considerations. So temperature, we're looking for high heat flow, high thermal gradients. A stratigraphy, we prefer a permeable geothermal reservoir. So, creating and keeping permeability wouldn't that be as big as a problem? And of course, the structure of the subsurface. Other considerations include access to transmission lines or power lines, the market, and of course, all kinds of socio-economic factors. So if you're familiar with the geology of the United States, you see that there's a very nice overlap between these high favorability locations and some of the major rift zones that we have. So there's the Basin and Range and Southern Basin and Range province that coincide with these redder areas. Towards the southwest, you can see the northern part of the onshore Gulf of California. And then here in New Mexico, the Rio Grande Rift Zone. And in the next few slides, I will talk about the Rio Grande Rift Zone. The next slide shows you an aerial photograph that I took from this portion of the Rio Grande Rift, looking towards the north-northwest. And here it is. So the entire area here, especially towards the right side of this photo, is the Rio Grande Rift Zone. And what you see towards the left is a large volcanic area. It's called the Jemez Mountains Volcanic Field. It started forming about 10 million years ago or so. And then within this Jemez Mountain Volcanic Field, you can see the Valle Caldera towards the left. This Valle Caldera formed about 1.2 million years ago as the result of a very large volcanic eruption. And interestingly, a few kilometers below the surface, below the Valle Caldera, is the top of a partially molten magma chamber. And then furthermore, I've indicated the town of Los Alamos and Los Alamos National Lab. So this was the location of one of the first engineered geothermal systems in the world. And this was done in the 1970s and 80s, and the system closed in the 1990s. So I'm going to walk you through some of the considerations for site selection of this geothermal site. So below the Valle Caldera, there's a very high thermal gradient. And I found this old study from 1986 that I'm showing you towards the left to give you an idea how the temperature here varies with depth. The vertical axis here is depth. Here's 500 meters, here quite at the top. And temperatures 500 meters below the surface here vary from about 100 degrees to 250 degrees Celsius. So these people were looking for very high geothermal gradients, what they found here. And this is the result of being, on top of this partially molten magma chamber. In this area, there's also a lot of hot springs. The map towards the right shows you the basins, the major sedimentary basins of the Rio Grande Rift Zone, and also the location of this, the location of the Jemez Mountains volcanic field with this Valle Caldera. And as you can see, it's at the moment we often sketch the rift zone towards the east of this Jemez Mountain volcanic field, but there are actually strong indications that the rift basins extend to below the volcanic field, and they've just been overprinted with this volcano in more recent times. So they're rift-related normal faults below the Via Caldera. So looking at the Via Caldera in a little bit more detail, you see here in a dashed white line the Via Caldera rim, and the yellow line here outlines a low seismic wave velocity zone in the upper crust, showing the location of this partially molten magma chamber. Now, for site selection, people looked at a lot of different things apart from geology. So permitting requirements, can we drill here? Are there roads available that we can drive to the site? Is there proximity to utilities and transmission lines? And then, of course, all kinds of geologic considerations, high heat flow, depth to the top of the basement. This caldera rim here, that's a series of ring faults, and we didn't want to be within that series. We didn't want to be within those faults because you don't want to reactivate them. But we still want to be sufficiently close to the magmatic heat source. So the location that was eventually chosen was actually not in the caldera, but just outside of the caldera. The work that was done for this geothermal energy in this region actually resulted in a lot of more in-depth knowledge on the evolution of this portion of the Rio Grande Rift, especially this original extension of the rift much further west to what is now below the Via Caldera. So to summarize this, I just wanted to give you take a step back and think about our research in terms of what it means for socio-economic impacts. So with the exploration and development of geothermal energy, geologic hydrogen, and carbon sequestration, the need for a thorough understanding of continental rifts has increased dramatically, and also on a much more precise and finer scale than we usually can do in our research. So the thermal structure, rheology, stress field, stratigraphy, subsidence and deformation histories need to be known in unprecedented detail to be economically successful and avoid hazards, leaks, or induced seismicity, etc. And that's all that I had for you today. Thank you.
Yeah, thank you very much, Jolante, for a wonderful presentation and the overview of what you've been doing. There's one question. I think we have run out of time. There's a question already on the chat by Cindy Ebinger. Great to highlight active rifts. Could you mention the circular economy approach to lithium and other mineral extraction from water as is being done in Arkansas?
Yeah, I can give a very short answer. So when you produce water in oil and gas fields, there's a lot of critical minerals in them, or there can be. Lithium is one of them. So what is being done now, and some of it's already being done in the field, perhaps not at a very large scale, is this produced water, when it's produced at the oil or gas well, it can be treated. So that means that we can, this is saline water, so we can take the saline component out, but we can also take out the lithium, for example. So we basically co-mine the produced water for critical minerals before either re-injecting it or perhaps treating it further and then using it for agriculture, for example. Yeah, that's an excellent question, Cindy. Thank you.